So I wanted to do a short video on sequence notation versus recursive notation or function notation of geometric sequences and series. So the first thing you should do is just maybe a compare and contrast between sequence notation and the recursive notation. They've both got this R, the common ratio, and they've both got this n-1 structure, which just means go to the term before. And what's a little less obvious in the recursive notation is they've both got information about the first term. So anytime that you're given a recursive formula, you'll always be given the first term as well as some constant ratio, and then you can use the recursive formulation to write out the sequence. And it's what you've been doing already in class, but it's formalized, kind of written down in the way that if you're entering it into a computer and you were doing a recursive algorithm in a computer, you would use this type of notation almost certainly. So in both cases, we have a first term, we have a common ratio, and then we have this n and n-1 structure where we're saying we're looking for a specific term and we're going to use the term that came before it, or in this case the number of terms that came before it, in order to find that term. So we'll do an example and we'll do it in both notations. So first with the sequence notation that we learned yesterday, then I think is maybe a little bit more straightforward. Given g sub 1, say that is 5, and a common ratio, maybe the common ratio is 10. Let's make it easy on ourselves. We can use this equation, this sequence notation of the geometric sequence, to write out the whole sequence or find a specific value in the sequence. So g sub n is going to equal the first term times the common ratio raised to the n-1 power. And then we could maybe, if we wanted to know g sub 10 or g sub 20, maybe g sub 15, we would just plug it in and it would be 5 times 10 and then to the 15 minus 1 power, which of course is 5 times 10 to the 14th power, which would be a 5 with 14 zeros after it, and I don't see any reason to write that out. This is you can call this leaving your answer in exponential form. Now let's look at this same sequence but using the recursive notation. We know g sub 1 is 5 and we know our common ratio is 10, so we're going to plug those values in for the recursive notation. So f of n is equal to the common ratio of 10 times f of n-1, and then we know that f of 1, the first term in the sequence, is the same as g sub 1 is 5. And this right here is what you would be given on a test question. It's what you'd enter into a computer if you wanted to compute the entire sequence. It's what you're doing intuitively when you write out the sequence by hand. So let's just follow this through. If I wanted to know f of 2, well, that would be, I would use this f of n formula. So that's 10 times f of n-1. So here's the substitution. The 2 is going to go in place of the n. So it's f of 2 minus 1. But f of 2 minus 1 is just 1. So that's 10 times f of 1. And now f of 1, we know that already because it was given to us in the first, we were told where we were going to start in our pattern. So then that is just 10 times 5, which is equal to 50. So there's the first two terms in our sequence. F of 1 is 5, f of 2 is 50. And if I wanted to go on and find f of 3, I would keep using this f of n. F of n equals 10 times f of n minus 1. And I would plug in 3 in place of n. But really all I'm going to be doing is going back and referencing the previous term. That's all this f of n minus 1 is doing. So that's going to be 10 times f of 3 minus 1. But we know that f of 3 minus 1 is really, or this the right side here is really 10 times f of 2. But we know that f of 2 is just saying, hey, go back to the term that you just found and multiply by 10 again. So that's going to be 10 times 50, because 50 is the value of f of 2. And then, of course, we could find the next value is 500. And at this point, you really should be able to see the pattern and realize that you're going to go 5, 50, 500, 5,000, 50,000, and so on and so forth.